In section 8.3, we're going to continue talking about rotational solids. We had previously talked about the disk method, and I'm going to start this with a little review so you see the difference between our new method, which is called the washer method, and what we talked about previously, which we called the disk method. You're going to use the disk method when your region is flush against the axis of rotation. So in this picture right here, my axis of rotation is the x-axis, and notice how this region is flush against it. So all points of it are in contact with that axis of rotation. And when I rotate it, I end up with this cone shape in the middle here. And if I were to look at any cross-section sliced perpendicular to the x-axis, it would be a solid circle that you see reflected over here. In the method we're going to talk about today, the washer method, our region is not flush against that axis of rotation. So my axis of rotation is the x-axis. My region is this triangular region. And you notice that I have a big space in between the two. So what's going to happen when I do that rotation right here, it's going to create a circle, a hole in the middle of this. So when I look at the cross sections, they're going to be shaped like washers because there's going to be a big hole in the middle that's created by this gap that's in between the axis of rotation and my region. My cross sections perpendicular to the x-axis in this case are shaped like washers, and that's why this is called the washer method. What we said in the last section and what we'll say in every single section in which we're finding volume is, in order to find the volume, we're going to integrate the cross-sectional area. So the fact that our cross-section has changed from a solid circle to a washer affects the formula that we're going to use. Our general volume formula is this one. We're going to integrate the cross-sectional area. A of x stands for the area. That is a broad general formula. So now when our cross-sections are washers, and I have a washer drawn out here for you, we have to find the area of what's shaded here. So I have two radii. One of them goes from the center to the outer circle, and I'm calling that by capital R. And one goes from the center to the inner circle, and that is my lowercase r. So if I want to find the area of this cross section, I do pi outer radius squared, give me the outer one, and then I have to subtract out the area of the whole, which is pi inner radius squared. And I see my common factor of pi that I'm going to factor out. And this is my cross-sectional area. So to find the volume, I'm just going to integrate that cross-sectional area. So my formula for the washer method is pi integral from a to b, outer radius squared minus the inner radius squared. And just like before, a to b is the x interval of the original region. And I have here that capital R is my outer radius. It's going to be farther away from the axis of rotation. And the lowercase r stands for inner radius. And you'll know that one because it's going to be closer to the axis of rotation. So let's jump in here and do one. And this is the actual region that we had drawn above for us. The directions say that S is the region bounded by the graphs of x equals -3, which is here, y equals 2, which is this horizontal line, and y equals -5/9x plus 16/3, which is this line here that's red. I went ahead and put a little subscript, and I'm calling that guy y1. And I'm asked to find the volume of the solid formed when I rotate this about the x-axis. So the x-axis is my axis of rotation. If it helps, you can do a little sketch of this. Nothing requires you to do that sketch, but sometimes it helps you to get your bearings. The first thing to do if you're going to sketch this is do a reflection across this axis of rotation. So each point is going to move the same distance to the opposite side. Let's trace out a few points to see if we can visualize this a little bit better. So this point that's up here, it's going to rotate around. It's going to bottom out right here and then rolls back up to the top. This point that's here is going to do a tighter circle because it's closer to that axis of rotation. A point, say right here, it's going to circle around. It's going to bottom out here and then come around the back side. And a point here is going to do a tighter circle around. And you can see these washers forming. So here's one representative washer. And what I can see is that this red curve, this y1, is rotating on the outside. And this y equals 2 is rotating on the inside. So y1 is my outer and y equals 2 is my inner. Because I see this gap here, I know that I'm going to use the washer method. Here is the general template for it. So pi, my limits are going to be the x interval of that original region. So it looks like it goes from a low x of -3 to a high x of 6. My outer radius, that capital R, is y sub 1. Since I've defined it as y sub 1 here, I don't need to write that whole function out. I can just call it by what I have defined it as. My inner radius, my lowercase r, is this y equals 2 that's rotating on the inside. And on my integral setup, it's pi, outer radius squared minus inner radius squared, and putting that into the calculator gives me 518.362 as my truncated answer, or 518.363. Let's take a look at another one. So in example number 2, I have region R bounded by the graphs of y equals x squared and y equals the square root of x. A good way to begin is just to get your bearings on this, figure out which graph is which, and I went ahead and labeled that on here. My axis of rotation is the x-axis, and I'm going to rotate it around this axis of rotation. Let's give this guy a little sketch. So the first thing I'm going to do is take region R and reflect it across that axis of rotation. Let's track a few points and see if that helps us visualize what's going on. I'm just going to pick a point right here. So this point is going to come around the front, bottoms out here, and then it goes around the back. And this point right here is going to come around the front, bottom out here, and then around to the back. Focusing on my washer here, I can see that my inner function is this x squared, and my outer function is that square root of x. If you have trouble visualizing this, just realize that you can start at your axis of rotation, move toward the region. Whichever graph you hit first will be your inner function, and whichever graph you hit second will be your outer function. Let's go ahead and set up our integral. Here is my general format for my washer, and I know I'm going to use a washer because I see the gap in between the axis and the region. My limits are going to go from 0 to this 1 right here. My outer function is the square root of x, and my inner function is x squared. Typing this into my calculator gives me 0.942 as my volume. Just like we did with the disk method, let's look what happens when that axis of rotation moves away from the x-axis to a different horizontal axis. And just like I did before, we're going to alter that radius by just subtracting whatever that axis of rotation is from the actual functions. Notice that at this point, this still says pi outer radius squared minus inner radius squared. So I'm still following the format of my washer. Let's take a look at this example right here. This is actually the same reason that we did in example 2 around the x-axis, but now we're going to change and have that axis of rotation be down here at y equals -1 and see what happens. So again, the first thing I want to do is figure out who's who. So I know that this red one is my x squared function and the blue one is the square root of x. Find your inner and outer the same way, and I don't even need to draw the actual solid. I can just start at my axis of rotation. I head toward the region. Whoever I hit first is inner. Whoever I hit second is outer. My limits haven't changed because my region still goes from a low x value of 0 to a high x value of 1. So my limits still go from 0 to 1. My formula up here says to find the function that's your outer function, which I've decided is the square root of x, and just subtract what your axis of rotation is, which is -1. And it looks like this. So f of x minus -1, because that's my axis of rotation, minus, and then the same thing using my x squared. These double negatives both turn into adding. And it gives me this as my integrand. And pretty much all I did was I followed this formula up here. But if you look at what this is saying about my picture, it makes sense. When I move my axis of rotation from the x-axis down here to y equals -1, what happened was I increased my radius by 1 because it was originally up here, and I just extended it down 1 unit. So now my radius increases by 1, and that's why here I've added 1 to both of these because that's increasing that radius. And then just putting this in my calculator gives me either one of these answers, truncated or rounded. Let's take a look at one more. And this one, again, I'm dealing with that same region as the previous two problems, but this time I'm going to rotate around y equals 2, which is up here. So just be careful in this one because even though it looks the same, there is one big difference in this one. So when I start at my axis of rotation, which is here at y equals 2, I'm going to head toward my region. The graph that I hit first is my inner function. And notice that this is the exact opposite of what was happening in the other ones. In the other two, the x squared was inner and the square root of x is outer. And for this one, they're actually switching places. And the one that's furthest away is outer. So make sure you always take the time to look at it graphically to determine which one is inner and outer. And once you've got that figured out, it pretty much flows like the other ones did. So my setup is pi. My limits again go from 0 to 1 because that region hasn't changed. This is my outer radius. So I determined that the x squared is rotating on the outside because it's farther away from my axis of rotation. And whatever this axis of rotation is, in this case y equals 2, you just subtract whatever that is from each of these. So my x squared minus 2 squared minus my inner radius is that square root of x minus my axis squared. And keep in mind this is still the same old washer method. Pi outer radius squared minus inner radius squared. I'm just subtracting that too because it's making an adjustment for that altered axis of rotation. From here I was going to put that in my calculator and I get my volume is 3.246.